Thank you very much. I would like to start by thanking the organizers for putting this together. It's been great so far, and also the scientific committee for the chance to talk. So let's get started by revising some very well-known facts about Grothendieck topoi. So I have a Grothendieck topoi G. I can put on it, consider it as a large site and put the canonical topology in it, which is nothing but the topology where covering families are the jointly epimorphic families. And we also know that Grothendieck topoi have a stable orthogonal factorization system given by epi mono. And so if we take this into account, we see that actually the canonical topology is fully determined by three pieces of data. First, we have the families of monos that are covering, so that are jointly epic. On the other hand, we have the single covering arrows, the epimorphisms, and the fact that they together form a topology is somehow codified by the stability under pullbacks. So we have covers like this, and we factor each arrow in our covering, and we get a cover given by monic arrows recomposed with single covering arrows. And if we look at the first piece of data, this points us in the direction of left cancellative sites, which are just Grothendieck sites in which every arrow is a monic. On the other hand, we can focus on the second and third piece of data, and this points us in the direction of atomic sites, right? Because if I have the category, the atomic topology is that every sieve which is non-empty covers, or that every arrow, single arrow, should cover. And so for that, I need an OR condition like this, with somehow the pullback stability is for us in general. And so why not put this framework now at the level of small sites? So let's see what we get. We define a covering monocyte as a Grothendieck site with its topology, together with an orthogonal factorization system, EM satisfying these three conditions. First, that the left class is included in the family of arrows that are single arrow coverings for this topology. Second, M is contained in the collection of monomorphisms. And then we have a nice behavior of the left class again with respect to itself. So we have an OR condition for morphisms in E, and also for morphisms in E with respect to the monomorphisms that are in my factorization. And so we can address already three kind of toy examples. First, if you take the left cancellative sites, just cut a site in which every arrow is monic. If I take the ISO and all arrows factorization system, this satisfies these three conditions. On the other hand, I can take atomic sites, and then again, now the other, like now take arrows as the left class and ISOs factorization system satisfies this, while the left quadrivality comes from the precisely that we have an atomic site. And then we have, in the case of a large site, we could consider the Grothendieck topos example we just did. And so you may say, why? I mean, if you restrict to this family of sites with this extra information, aren't you being too restrictive? Don't we lose information regarding topoi? And well, we can prove that's not the case. For every topos, we can find a covering monocyte presenting it via sheets. Very sketchy. We have, I don't know, left and right, it's always a mess. And you just take any site presenting your topos, and you consider the morphism just taking your head and then should be fine. And so we see we take the essential image of B inside our topos, and first we close it under finite limits, and afterwards we just factorize epi mono inside the topos, and we add the sub-objects that we obtained there. Because topoi are well-powered, this remains small, and we put the topology, the induced topology on this, and this will be a covering monosite. So we can present topoi using this type of sites. And we can also define the suitable morphisms for them, which will be morphisms of sites, so covering preserving, and covering flat. But in addition, we impose that they send the left class to the left class and the right class to the right class. And so we will denote CM site for the two categories of sites with these morphisms. And so this statement that you say, okay, we recover at the level of objects on topoi can be pushed actually to a two categorical statement. And for that, I need lambda comparison maps. So morphism of sites, no further assumptions. We call it LC from lambda comparison. If it is covered reflective, and in addition satisfies three properties, which I won't enter into details, but they are, first of all, I can cover every object by something coming from the first, and the second one by something coming from the first. And then my factor F will be full and faithful up to cover. So I mean, this is written technically here, but that's basically the idea. And so we have the following theorem. If I take this two category of covered monocytes, I take the pseudo factor, we know it in objects, just taking shifts. I won't enter into the details of the morphisms and the two sets, but then this pseudo factor will send the lambda comparison covering monomorphisms to equivalences in the double loop, if you want, of Grothendieck topoi. And this actually witnesses that we can express this two category as a bicategory of fractions of this one by inverting this morphism. And how do we prove this? So basically, we use the factor forgetting that we have covering monocytes, and we already have this result for sites and LC morphisms. So, yeah.
For what is this called? What does it stand for?
It's called, how did he say it? It was conjugate opposite. I have to look it up every time. So conjugate is you reverse the direction of the two morphisms and opposite the direction of the one.
Yeah.
Okay. And so we do have that these covering monocytes allow us to recover like two categorically the category of Grothendieck topoi. And so we have more or less this picture. On one hand, we have the left cancellative sites, which are, as we saw, a subclass of covered monocytes. On the other end of the spectrum, we have the atomic guys. We know that left cancellative sites give us étendues, atomic sites, atomic topoi, and we know they present all Grothendieck topoi. Okay, so in a way, we can see Grothendieck topoi as some sort of interpolation between atomic topoi and étendues. This is a very vague statement. We are working on making this more precise. And Dorette, which we'll be talking next, and she will be talking on the second part of this story, will give a couple of more hints to things we can look at, but this is work in progress. Okay, but now, here we have étendues and left cancellative sites. And in the inverse semi-group theory community, this has been studied thoroughly. And we have a correspondence between left cancellative sites and resonant sites that was first studied by Lawson and Steinberg and then further analyzed by Dorette and Larry. And so the thing is, in here we would like to have a framework that contains resonant sites that allows us to present any Grothendieck topos. And so for doing that, let me analyze what resonant sites are a little bit. So an ordered groupoid is just a groupoid internal to the category of full sets, such that the source map is a discrete vibration. And if we express it double categorically, we have two cells like this, in which the objects are given by the objects of the poset of objects. The vertical arrows are given by the order in the poset of objects. Then the objects in the poset of arrows are the horizontal arrows, which are isos because we have a groupoid. And then the double cells are given by the order in the poset of arrows. And the vibration, the discrete vibration property is given like this. For every such corner, we can find a unique cell that fills it in. So similar to the restrictions I was mentioning now, but we only have corners. And this indeed is called the restriction of F to A. Okay, so now we have ordered groupoids, and we can put Ehresmann topology on them, which is very much translating the axioms of Grothendieck topologies to this framework. So we have vertical sieves, which are just ideals in posital sense. So they are down-closed subsets of the down set of A. And they have to satisfy the usual properties. So first, the whole down set should be covering, should be my topology. Then we have the pullback property. So if I have something in my topology, I pull it back along here, then it should be in my topology. And the pullback is basically doing this. You take all the vertical arrows on top of B, such that when I take the restriction, at this composition here, the vertical composition on the right, is in S. And now we have the local character. As usual, we have, if I have a covering sieve and any sieve, if I pull back along elements in the covering one, and I get something in the topology, then the sieve should be initially in the topology. And so we call an Ehresmann site a groupoid, an ordered groupoid with the topology. Okay? And we can also define sheaves in this framework. For that, we need compatible families. The intuition is the same as incompatible families for Grothendieck topoi, but we have to handle now vertical families of vertical arrows. And so if I have a double functor, now instead of three sheaves, I have double functors, namely in the double category of sets in which both horizontal and vertical are functions, and then two cells are commutative squares. Then we say that the family of elements in F of AI are compatible for this double functor and this family. If in the case that I have a B on top of two of those, then Xi gets sent to the same place as Xj. Okay? And now we can define also sheaves like this. So they are double functors such that for every covering sieve and every compatible family of that covering sieve, there exists a unique gluing. Okay? And morphisms of sheaves are just vertical natural transformations of double functors. Equivalently horizontal, because an EQ set is extremely symmetrical, so they are the same. They are equivalent. And so Lossen-Stenger and then Torres and Variant further proved. I mean, there's a construction in which you can associate each element site, a left cancellative site, with the same category of sheaves. And we know the sheaves of left cancellative sites are étendues. So we know that Ehresmann sites have represent étendues. And then we have the reverse construction. To every left cancellative site, I can associate an Ehresmann site. They have the same categories of sheaves, and we know, by work of Rosenthal, we know if this is true for every left cancellative site, the sheaves are étendu. From work of Koch-Murdek, we know that the reverse is true. For every étendu, I have representation in terms of a left cancellative site. And so with this, together with this statement, we know every étendu can be presented as sheaves over some Ehresmann site. So now we want to copy this. And by the way, of course, I have to mention this is only of objects, and I didn't give the construction. And this was first one categorically introduced by Losman standard, and Grothendieck made this whole story into a categorical picture, but I won't enter into more things here. Let's see how we can generalize this to try to present all topoi. So now we replace groupoids by categories. So we just consider order categories, internal categories in the category concepts, and we keep the discrete vibration property. So double categorically, we have the same picture. We have, with the only exception that of course now we don't have the groupoid, so the horizontal arrows are no longer iso, the discrete vibration property. And now the idea, the heuristics behind this is now, I don't want my arrows to be isos, but I want to see them as single covering arrows. Okay? And so for that, for single covering arrows to have some topological information, we need, like in the case of atomic topoi, some sort of OR condition. So that's what we have here. We say order category is left quadruple. If for every such diagram, here is vertical, horizontal, and here just two horizontal arrows, we can find fillings here as a 2-cell and here commutative diagram. These are not unique, they just have to exist. Okay? And now we can endow such a creature with Nearsman topology as before. And we can also define sheaves. But now we have some topological horizontal information. So I have defined compatibility for vertical arrows. I need now compatibility for single horizontal arrows, and that's this definition here. It's self-compatible for F and this single arrow if I have two arrows starting from C and landing in B, such that if I restrict to, I compose with F, so compose with the restriction of here of F. They are the same, then they have to be sent by F from here to here to the same piece. And with that we can define sheaves in the very same way. So first unique fluid for vertical arrows, vertical families, and then unique fluid for horizontal arrows. And the morphisms, again, the same as before. And what we prove is that we can associate first what we build from any covering monocyte a generalized personal site as follows. Objects are equivalence classes of monos, which has monos only in my right class. Okay, so sub-objects that come from monos in my right class. Vertical arrows are the usual less or equal relation of sub-objects. So this, if there exists an arrow here. Horizontal arrows are given by equivalence classes of things like this, where my M prime is something related to my M. My N prime is something related to my N, and then they are connected like this to an arrow in the left class. And see that we can actually always consider the N prime to be equal to M, and then we take the arrow to be the horizontal composite here. So we can always consider that special representative makes my life easier, especially if you introduce two cells, which will be, here we have the horizontal arrow, this the top one, the bottom one here, and this is the lesser equal of this one. This is, sorry, went too far. And this is the the right arrow here, and this has to commute. And for the left quadrivality, we obtain it from the one from our orthogonal factorization system, and the discrete calibration comes from the fact that our factorization is unique up to isomorphism. And we put the topology in it. And so the covering families will be families like this, such that the arrows that give me that they are less or equal were covering before. And we can go the way round. We take generalized Ramos sites, and we can associate the covering monocyte. This one is easier. Same objects. Arrows, formal composites, composites of horizontal vertical, where the composition is given by the discrete vibration property. The topology, we consider families like this, in which the vertical part was covering in my Ehresmann topology. And then the factorization system in this site will be taking horizontal identity and isomorphism vertically. And the left quadruplicity follows almost directly from the monophy. And so with this, we can actually prove that if I start for covering mono and I go to generalized Ehresmann, I recover the same site, and the same the other way around. And so this story is at the level of objects. Dorette in a couple of minutes will be telling you at the level of morphisms. And so we have the picture filled in, where now our atomic topoi correspond to generalized Ehresmann sites where every vertical arrow is an identity. And to finish, I would like to have a slide on what was our motivation when we started to do all of this, which was to try to understand Grothendieck in a two-categorical perspective. So we have these results, right? But if we restrict to left cancellative sites and we take sheets, can we actually invert here LC morphisms as well in order to obtain a bicategory of fractions? And the answer is it is too small for these particular morphisms to have a nice calculus of fractions. And so we have to enlarge. And inspired by the work of Koch and Murdek in presentations of Grothendieck, we have left cancellative and Ehresmann sites in correspondence. We can consider covering monocytes, which every morphism is locally monic, meaning they may not be monic, but there's a covering that makes them monic, and they correspond nicely to something on the other side. This is still not big enough. We need another step, and this is torsion-free generated, meaning a torsion-free object is something that every arrow landing on it will be locally monic. And torsion-free generated means that every object in my site is covered by torsion-free objects. And there's a correspondence on the other side, and these guys will meet the calculus of fractions that allows us to recover the two-category of continuums. And with that.
Thank you for the talk. Questions, remarks?
Yeah, good. Thanks for the talk. Can I ask how this relates to the topological groupoid presentation of autolysis? Because you have this ordered groupoid and it's a discrete vibration. It looks like it's a local homomorphism groupoid.
We would like to look into that. It's something like for future work, and Dorette probably can say more than I can on this, but yeah, it feels indeed related, but up to this point I cannot say much more. It's something to definitely to explore further. Thank you. Yeah.
Further questions?
Well, what makes these sites easier to work for? I mean,
the funny thing is the sites, they don't become easier to work, but the Ehresmann sites are very easy to work. So, in a way, you can, the double categorical part is very nice to work with. We have the information very nicely separated, the interaction between the two parts is very nicely codified, so then it is they are very handy to really manipulate in that sense. So, we wanted to see what's the interplay with the site, the Grothendieck site part of the story, but in there I don't see much more of an advantage of considering these particular sites, either than they give us presentations and they allow us to go to the double categorical setup. Yeah, go ahead.
I think my slide.
Okay.
Answer the question.
More questions? Remarks?
Okay. How the construction of this covering monocyte for topos relates to the closed mono, dense mono, closed mono construction? Because it looks a bit like the factorization system you get with the closed mono on the right and epi and the dense mono is a bit like the factorization condition on your the factorization system you consider on your covering monocyte. No?
I don't know actually. Haven't thought of.
If you take the category of pre-sheets, visual topology, and consider on it this factorization system, epi, dense mono, monocyte, and closed mono, do you think it gives rise to an instance of a large covering monocyte?
It's a nice question. I haven't thought about it. I would suspect you can get definitely to some of our examples, but I don't know if it's a direct, if I have to do some manipulation on it before. I'm not sure, I would have to look into it, but thanks.
If there are no further questions, let's thank the speaker again.